Assalamualaikum. Okay. Assalamualaikum students. Hope you are well. So in this video lecture we will start with chapter number 2, which is a question of state. In the question of state, what we are saying, why it's important, as I told you before, in question of state is basically is like if you look at your ideal gas law, you have ideal gas law, okay, which is PV equal to nRT. Now this is your ideal gas law. Ideal gas law works only if you are thinking that your system is behave ideally. And what do you mean by system behave ideally? What do you mean by ideal system is like you have no interaction between the molecules. Okay, so there is no interaction between the molecules. For example, you have molecule 1 and molecule 2. There is no interaction between the molecules. In ideal gas law, this is one, you are assuming that you have no interaction between the molecules. The second thing you are assuming is there is no molecular volume. No molecular volume. This is the second thing that you are assuming. It means like this is your molecule, right? Now they don't have any molecular volume in real gas system. No molecular volume. Okay, obviously these two assumptions does not work in a real system. So when you have a certain thing uh, which says like there's no molecular interaction and no molecular volume, then you can say this is not possible in a real system, in a real environment. So what you have in the real environment is basically you must have in the real system, if you're considering a real system. So in the real environment, the real system, you must have molecular interaction. Molecule does interact with each other. And second is you must have molecular volume. Molecules does have some volume. Okay, what this means is in this one, if you are compressing a gas, you can compress the gas to a limit where they have molecular volume. You cannot compress it more than this. For example, these molecules are here and here. If you want to compress them together, you can compress until this point. After this point you cannot compress them because molecules have some volume between them. Okay, so this is the what we have in the real system. So what the question of state is doing basically is they are actually showing you question of states or US. Okay, they are showing you, they are basically correcting this real gas law, which is this is your real law. This is the question of state, but this is the real gas law. The real question of states, what they are doing basically is they are adding the interaction of the molecules. Okay, they are adding the interaction and they are adding the molecular volume. So they are correcting two things. One is the interaction between the molecules, another is the molecular other is the molecular volume. So in this question of in this chapter also, what we are focusing on is how the real gas law behaves and what are the things that has been changed in ideal gas law and that is being used in this question of state, and how this addition of these two things will helps to calculate the different thermophysical properties. So solving a question of state allow us to find specific volume. This is what our focus is. You want, obviously when you're talking about real gas law, real gas only applies when you have a mixture. If you have a pure system, then obviously there is no between one component or between one molecules, there is no interaction, right? The interaction only comes when you have, so if this is your molecule, only one molecule, pure component. If you have pure component, then in pure component you basically have no interaction, because the interaction, for the interaction you must have some other molecules. Where is the other molecule? Okay, but if you have multiple components, okay, you have two components or you have multiple components, right? So there is definitely an interaction between the molecules. This interaction will help us to calculate the specific volume, the volume of that component which is specific to that component. Okay, but for pure components you don't have these things. Okay, for specific volume it only comes when you have a gas mixture. Okay, this is the first thing of a chemical at a specific temperature and pressure. So what is the specific volume of the gas mixture at specified temperature, at the given temperature or at the given pressure? This is what you need to find out. Without using a question of state, it would be virtually impossible for us to design a chemical plant. This is very, very important. To design a chemical plant, you need a real system. For a real system to apply, you must have a real equation of state. You cannot apply or cannot use ideal gas equation for a real system. To design a chemical plant, you must need a real equation of state. So by knowing the specific volume, okay, we can determine the size and the cost of the plant. So real equation of state gives you many different physical properties. By knowing those physical properties, you are able to find out the size of the equipment, how you can size the equipment, how you can construct the design, and what is the cost looks like. Okay, this is very, very important. It only comes when you have when you know the specific volume. The specific volume you only able to know when you have a real gas equation. Your ideal gas equation you cannot, you are unable to calculate the what you called the specific volume. So HYSYS, what HYSYS helps you, HYSYS can give you many different equation of states. The one which we are focusing in this whole course, particularly or mostly we use these two equation of state. One is called Springer-Robinson equation of state, which you already know from previous chapters, and the other one is called Sauve-Redlich-Cohang equation of state, or SRK equation of state. Short we can call SRK, or in short for Ping-Robinson we can call Ping-Robinson, PR. Of these, Ping-Robinson equation of state supports the widest range of operating condition and great variety of system. Between these two, the most popular one is used, and it is developed by a petroleum company in Canada, and they support a great range of operating conditions. Okay, means like they can be practically more applicable as compared to SRK equation of system. So the Ping-Robinson equation of state and SRK are Sauve-Redlich-Cohang. Sauve is one scientist, Redlich is another scientist, and Cohang is a third scientist. With the collaboration of these three scientists, they developed Sauve-Redlich-Cohang equation of state, which is known as SRK. So Ping-Robinson and SRK equation of state generate all the required equilibrium and thermophysical properties. So they can generate, or they can provide you all the equilibrium and thermodynamic or thermophysical properties, okay, which you need for sizing the equipment and costing of the equipment. So the Ping-Robinson and SRK package contain enhanced binary interaction parameter. This is most important. Okay, whenever you talk about the real gas equation, it means like they are focusing on two things. One thing I told you before is the between the interaction between the molecules. This is the first thing they focus on. The second is they focus on molecular volume. Okay, so if they focus on these two things, then they follow the main rule. Okay, so you know that the interaction only comes when you have components more than one. So if you have one component here, another component here, this is binary component, right? So this interaction is called binary interaction parameter, BIP, or binary interaction parameter. It only comes when you have more than one component. So if you have normally it is mentioned for binary components because only binary components can have interaction. The minimum is binary components that can have interaction. So what SRK and Ping Robinson do, they have the enhanced binary interaction parameters inside their library. Okay, so they have the interaction, they are considering the binary interaction parameter, and for all the library of hydrocarbon pairs and non-hydrocarbon pairs. Okay, hydrocarbon pairs means you have gases, different gases. What is the interaction? Let's say if you have two gases, if you have ethane, methane, and if you have ethane. Now the ethane molecules are different than ethane molecules, and how the interaction between these two components will be affected. Okay, how this, so the interaction is known as binary interaction parameter of for methane and ethane. This binary interaction parameter uh, is important for a real gas system. Okay, so let's go back to the so we can see that and this Ping Robinson and SRK, they have the hydrocarbon interaction and pairs. So we have the binary interaction parameters for hydrocarbon pairs. A combination of fitted and generated interaction parameters as well as for most hydrocarbon and non-hydrocarbons. So they not only have for hydrocarbon, they also have for non-hydrocarbon also. So this is what is important. So the first thing they must tackle this problem, that in what idle gas is showing that there's no interaction, but in real cases we must have a interaction between the molecules. So Ping Robinson and SRK is basically addressing the first part, that they must have an interaction between the molecule. The second thing is that they determine the specific volume of the gas mixture of chemical and so in this chapter what we are focusing on, how to calculate the specific volume of our different gas mixtures by using Ping Robinson and SRK equation of state. These are the two things that we need to focus on by calculating the specific volume of a gaseous mixture by using Ping Robinson or SRK equation of state. Okay, so the outcome of this chapter will be to determine the specific volume of a pure component or a gas mixture with HYSYS. This is what you need to do. Either you can calculate the specific volume of a pure component, or you can calculate the specific volume of a gas mixture. Okay. Secondly, we are using two different equation of states to calculate the specific volume, so we need to compare the specific volume between each of them. Okay, how the first one will calculate the specific volume and how the second one is calculating the specific volume, and then we can compare the difference between the results. Second and third thing is we need to preview the results using a workbook, and we analyze the property using a case study. We will talk about case study also in this chapter, because case study play a very important role. Okay, so we study how if you change one parameter and how this will affect the other parameter on a diagram. If you are trying, for example, if you say you have a pressure and volume relationship, how the diagram looks like, either it is increasing or it is decreasing. This will be shown up in case study. So we will do case study to understand this part. Okay, so let's start with the HYSYS. And the first thing, as I told you before you start HYSYS, you start a HYSYS and you need to select the components. Okay, and then you can define the fluid package, and then you can define the material stream. These are the four things that you always follow whenever you start a new simulation. So before I jump into a calculation step, a little bit overview of what is the real gas law and how it is different, how the real gas law is different from ideal gas law. If you see on your screen, you have a ideal gas law that is mentioned, that is shown. So PV is equal to nRT. If you divide both sides with n, you will get specific volume. okay, which is represented by V, or molar volume. You can say molar volume also. Molar volume, it's easy to understand. So molar volume for each component. Molar volume is nothing but the volume divided by the number of mole of that component. The term P in absolute pressure, here the P is absolute pressure, V is the volume, N is the number of mole if moles, R is the gas constant, and T is the absolute temperature. Okay, the unit of R have to be appropriate for the unit chosen. It depends on the value of R is based on what units you choose for temperature, pressure, and volume. This equation is quite adequate when the pressure is low. You can see here in this equation is variable. You can use this equation only if your pressure is low. What do you mean by pressure is low? When the pressure is low in the system, your molecules doesn't behave, the molecules are very far from each other. Gas molecules I'm talking about, the gas molecules are very far from each other. It means like there is no interaction. We can assume that in that case, if the molecules are very far from each other, there is no interaction between the molecules. And since the molecules are very far from each other, we are considering that the molecular volume is negligible, or nothing is there, because there is nothing for interaction, there is nothing to compress. This is only when happens when your pressure is low. At low pressure, you can assume that at low pressure your molecules behave ideally. So you can think that okay, at low pressure we can apply the real gas law, there's no problem. Okay, but real gas law only applicable if you start increasing the pressure. What happened when you increase the pressure? At high pressure, your molecules come very close to each other. When they come very close to each other, it means like now there is an interaction between the molecules that will step up. Okay, now you can consider that there is an interaction between the molecules, and now you can think, you can say that you can compress the molecules to a limit when you have a molecular volume. Okay, so at high pressure you can always expect the real gas law to be followed, but at low pressure you can assume that. So at low pressure what you have, so low pressure molecules are far from each other, let me clear this. The molecules are far from each other. Okay, so there is no interaction in that case, or we can simply assume that there's no interaction between the molecules because molecules are far from each other at low pressure. Okay, this is what we have first time. Second thing is, when they are very far from each other, there is no point of adding the molecular volume or thinking about molecular volume. So there is no molecular volume in that case also. Okay, so these are the two things. If there is no molecular volume and no interaction, then we can simply assume we can use ideal gas law. Okay, or you can just apply here, this become the ideal gas law that you can use if they are very far at low pressure. Okay, particularly at low pressure. However, at higher pressure you cannot assume like this. At higher pressure, the equation of state, other equation of state have been developed to address the chemical. So at higher pressure you have totally different scenario, totally different situation. So at higher pressure you can say we definitely have some molecular interaction, and then you definitely have some. So in case of at higher pressure, what you have, you have this equation. You can see here the pressure volume relationship is now totally different. What you have in this particular case, you added this term B What is B? B is the molecular volume. So what this basically means, when you are trying to compress the gas molecules to a certain stage, for example, this is your molecules are far from each other, right? If you compress the molecules and if they come to a position which is like this, then you cannot compress it further because there is a molecular volume called B. So what they basically did here in this example, in this formula, they added molecular volume with, and they minus this one, subtract this with the volume of the whole system. So when you subtract the volume of the whole system with the molecular volume, then you can think that this whole is the volume that you can use instead of only molecular volume. Okay, only system volume. So instead of using only system volume, you can subtract this with molecular volume to consider that as a whole, as a volume. Similarly, they add A. What is A? A is the interaction between the molecules. Okay, so there's an interaction between the molecules. This interaction that is represented by A. So these two things that is basically missing in the real gas law, they added these two things to complete the gas law, and this uh, real gas law was first developed by van der Waals. That's why it is called van der Waals equation of state. So this is the start they're taken by van der Waals, and they are saying that there's definitely a molecular volume and there's definitely an interaction between the molecules. This extension is just first step, however, because it will not be a good approximation at extremely high pressure. Now, this equation is okay for higher pressures, but very high pressure, extremely high pressure, still this equation of state suffers. That's why a scientist called Redlich and Kohong, they come in and they do some modification in this equation, okay, to improve the equation of state. And once they improve the equation of state, they call this with their own name. They call this van der Waals equation of state with their own name, and that is called Redlich-Kohong equation of state, or SRK equation of state, because they did some modification with this equation of state. But the problem with this equation of state at that particular time is they can only be used in one process. You cannot use it for multiple processes. Then a few scientists, they work on a similar situation. They take the basis of the SRK equation of state and they start modifying it, and they come up with the equation of state that is more presentable, or that can be used in many different processes instead of using one process, and that is called Ping-Robinson equation of state, or a PR equation of state. So this is how the equation of state basically emerged. Since from ideal gas law, the van der Waals equation came. From van der Waals equation, the SRK equation came, and then from SRK equation of state, we have what you call the Ping-Robinson equations. So the development process took like from van der Waals equation of state. So if you look at this table, basically this table is show you the comparison between the SRK, or Redlich-Kohong equation of state and between the Ping-Robinson equation of state. So these are the two comparisons that is done. If you look at the comparison study, if you can see here, this part of the equation of state, this part is almost similar. Okay, so what they basically means, like the molecular volume, you're considering the molecular volume is fine. There is no problem with the molecular volume. You're considering, you're adding a molecular volume, so this part is correct, totally correct. However, at low pressure to a higher pressure to extremely higher pressure, what happens is the interaction between the molecules, they differ. So this A is basically the one which is changing whenever you're using higher pressure. Okay, but Redlich-Kohong equation of state, they are okay with high pressures, but with extremely high pressure, again they suffer. So what Ping-Robinson did, basically, they cannot change this part because they are saying like definitely there is interaction, but how this interaction will behave when they with the molecules when they are high pressure. So this part they modify and they are basically add to this part. Okay, so what this says is like not only there's a addition of volume with the molar volume with the height multiplied by the molar volume with at high pressure, but there's also subtraction of the volume with molar volume multiplied with the volume. So this part he added here in he basically modified in SRK equation of state this part. So once they add this part, then you can use this equation of state for multiple systems, especially for a system which contains high pressure. Now higher pressure gases compressibility also differs. So for gas compressibility they define equation to calculate the gas compressibility. They define this equation. Similarly, if you want to use Ping-Robinson, the gas compressibility can be defined with find out from this equation. So these two equations can be used, this one for SRK and this one for Ping-Robinson, to calculate the gas compressibility, because gas compressibility also play a very important role. Okay, fine. Now this is okay for a pure system, but if you have a multiple system, then you use this equation. Okay, you need to multiply with the composition and add them together to find out the overall volume. So for gas mixture, instead of using B, you use this whole term. You need to sum up all the composition and the molar volumes. Similar equation can be used here. Nothing is changed in Ping-Robinson. For in this case, if you want to find out the volume for the one component, how you can find out the volume of the one component? So they reach to a conclusion that you can find out the volume of the component by using its critical properties like TC1 or PC1, and then you can add some kind of constant to modify that properties and give you a volume of the molecular volume of the component. Okay, so by using the critical temperature and critical pressure multiply with the gas constant with some constant also here, they are able to find out the molecular volume of a component. Similarly done by here, but here the constant they use is different, and this constant what they use is depend on the experimental value. Okay, so they optimize this constant and this constant based on their experimentation, not like this. Okay, now this is for molecular volume, this is for molecular volume, that is fine. Now what about the interaction? We need to know how much is the interaction, how we can define the interaction. So what they did basically, they did double sum of the mole fraction and the molecular volumes, molecular interaction between the two components, and they add the term binary interaction parameter, which is represented by Kij. What is I and J means basically, if you have like two components, let me show you on the screen. If you have ethane and you have ethane, similarly if you have methane here and ethane here, so this row we can represent by I and this row we can represent by J. Okay, so I and J means if you say the interaction between I and J. Okay, so let's say this is J1 and this is J2, and similarly I1 and I2. If I ask you, is there any interaction between I1 and J1? I1 and J1 is mean similar molecules. Okay, if they are similar molecules, then there is no interaction between the molecules, no interaction. But if I say, do you have any interaction between I1 and J2? Definitely you have some kind of interaction here because they are different molecules. Okay, similarly if you say here, is there interaction between J1 and I2? Definitely there's two different molecules. But if you say, this is like a graph, okay, like a table, like you can say here like this, okay. If you have a molecular interaction between I2 and J2, no, because they are similar molecules. So what this I and J means is the interaction between this is the mole fraction of component I, Okay, first component, this is the mole fraction of component B. Let's say in this example, mole fraction of methane, mole fraction of ethane, the interaction of methane and interaction of ethane. Similarly, it is basically a square root. Then you multiply this with the multiply with 1 minus binding interaction parameter. So when molecules there's no interaction, then this part will be 0. Okay, or this one will be 1, not 0. But if there is an interaction between molecules, then it has to be subtracted from 1. So it means like when there is no interaction, the molecules will behave ideally, then you have only 1 here. But if there is interaction, then you need to subtract that interaction from 1, so that it will be added or subtracted from your interaction, overall interaction. Similar equation is used here. Okay, similar equation is used here. Nothing has been changed. For individual interaction, you use this formula, ACI and alpha I. Okay, similar equation is used here. For ACI, interaction of component 1, you need to use this one. Again, you need to know how is the interaction, and you need to relate this one with someone. So what they did is they basically relate this one in critical properties like critical temperature and critical pressure, multiply with R, square up, and then multiply with this term with this number. This number is optimized based on experimental value. Similarly to use here, but here also they do some modification with interaction, and they use slight difference in interaction this parameter with this parameter. Okay, now this is done. Now what is left is alpha. So what is alpha here? Alpha is, they represent alpha in terms of their reduced temperature. Okay, and they add some m term here. M is eccentric. M is basically, again they will define the m in terms of their eccentric parameter. Eccentricity or eccentric parameter is the molecular shape, how the molecule looks like. For example, if the molecule look like circular shape, or they are oval in shape, or they have some kind of curves on their surface, all this is molecular shape. This is represented by eccentricity or gamma, or not gamma, you can say this kind of omega. Okay, so this is how they create one by one term to define each component. What is the idea? The idea is to clearly define what is the molecular volume. Is there any equation that is basically give you molecular volume of individual component or gas mixture? Is there how you can define, or what equation is used to clearly define the interaction between the molecules? These two terms need to be clearly defined in terms of equations, so that you are able to calculate. Similarly, if you look at your Z, in Z you have A, B, and B square. What is this thing? Okay, how you can find out? They again give you equation for this one, where they relate A with the interaction between the molecules times the pressure divided by RT square. Okay, similar equation is used in this form. And for B, you relate this one with the molecular volume B times the pressure divided by RT. Similarly, it is used here also. So what is the idea? The idea is like both equation of states can be used for a system, but Robinson equation of state is used mostly for different systems, but purely for gas systems, because they can give you good result at higher pressure also, as compared to Sovereign-Cohen equation of state. So we have two different equation of state. One is SRK equation of state, other is Robinson equation of state. To start with the simulation, what we need to do, we will start with SRK equation of state, and we will choose the component called N-butane. Okay, N-butane we need to choose for this component. So our fluid package is SRK equation of state, and our component is normal butane. The information for the stream that is given to us here is the stream name is 1. You can rename it with different name also. The temperature for the stream is 500 Kelvin. The pressure is 18 atmospheric. The composition, since it's only pure component, one component, so the composition for the pure component is just 1. And it is given in terms of molar flow is given in terms of kg mole per hour, not kg mole per kg per hour, kg mole per hour. So we have molar relationships. Okay, so let's start with the simulation and see how it works. Okay, Again, you need to select the component. So component that we need to select in this case is pure normal butane. It is shown up here. Okay, if it is not shown up here, then you can always search normal butane. We need to add, click on add normal butane, it will be added here. So the component is selected. Second we need to add is the fluid package. The fluid package in this case, in this example, we need to use is so red Kohang, or in short SRK. Okay, so you select this component, you select the component list, you select the fluid package, done. Now you can go to simulation environment. So in the simulation environment, what we will do, the first thing we do is to select the material stream. We select the material stream, we can put them in the middle. Since it here the name is not defined, so we leave it like this. You can change it this one also, but if you can leave it like this. If you open this one, you can see here the temperature by default is given in terms of degrees Celsius. We can change it here also, but I will try, it is better to do it here on the unit set. So we go up in the unit set again, and we need to find out where is the temperature. Temperature is mentioned here. We change the degree Celsius into Kelvin, and then we can click on OK. Pressure is ATM, that is fine. So the temperature that is given is 500 Kelvin. I type it 500 Kelvin. The pressure is mentioned 18 atmospheric, so click on 18 atmospheric. Molar flow rate is mentioned 100 kg per hour. If it is not mentioned, then you can assume 100 kg per hour. And the final thing that we need to define is the composition. Since it is only one component, so the overall composition has to be 1. And since we are using molar flow, so it has to stay on molar fraction, not on mass fraction. Okay, if it is shown here 100 kg per hour, which is mass flow rate, then we need to switch to mass fraction. Since it is not, it is only it is showing 100 kg mole per hour, so we are stick to mole fraction. Click OK, and then it is it is basically done. But what we need to do in this particular case is if you look at here, if you go inside and if you go to properties window, or if you stay on conditions, normally what you do, you need to find out the unknowns here. But if you look at on this table, this sheeting, flow sheeting, here we don't have any. So if you look at on this the list, what we are asked to do in the question in this example is we need to find out the specific volume. For in Aspen HYSYS case, it is called molar volume. So we don't have any molar volume on this list. Okay, so how we will find out the molar volume? And it is not added on the worksheet. So what we need to do, we need to close this one. To find out the molar volume, what we need to do is we need to go to the workbook, which is shown on the top, just like an Excel sheet. Okay, so again the same kind of properties are shown up here, but again there's no molar flow rate. Okay, or there's no specific flow rate. Then what we need to do is to set up this sheet, we need to go on, click on setup. So once you click on the setup, you will see this window. Now here either you can find out, if you want to find out the material stream properties, or you want to find out the composition, you want to find out the energy stream properties, or if you want to find out any unit operations that is shown up here, or you want to add any unit operation properties here. Okay, obviously for us we are only considering material stream right now. So what we need to do, we need to add a material stream, and we need to search here. For you, maybe this search bar is not not open or not there. Okay, but you need to go down and find out where is the molar volume. Or in my case, I can search molar volume, and I can just click on this molar volume and then add. Okay, and then done. So once you're done, molar volume is added here, and also molar volume is added on your workbook. You can see here the molar volume information is given here, the answer for your question. In feet cube per pound mole, the answer is 32.97, and if you just scroll it on the top, you can see here in terms of meter cube per kg mole, it is 2.058. Okay, this is the answer for your question number, for this for this example that is asked. Okay, so this is how you can find out the specific volume or molar volume for what you call molar volume for any gas mixture. In this particular case, we are focusing on pure components, but you can use it for multiple components also. Okay, this is one way. Okay, one way how you can find out the molar volume by going into workbook and then you can add molar volume here. This is one thing. The second thing, which is the second way you can find out the molar volume, is if you want to show the result of the molar volume on some kind of a table. Like for example, here you can see here this is only just one arrow which doesn't show anything, but if you want to show some properties on this as a table on this screen, how you can do this. So what you need to do is you need to click on right click, you need to right click, and then you can, if you go down, you can have an option called show table. Just click on the show table, and by default it will give you some table which have some information that's mentioned. What I want from this table to show is only the specific volume, not the temperature, pressure, molar flow rate of the stream. Okay, so what you need to do is you need to double click on this table, and you can see here by default the temperature, pressure, molar flow rate is given. I don't want these three things, so what I need to do, I just remove those three things. Once you remove those three things, now you want to add, what you want to add is you want to add molar volume. Okay, which you want this table to show up. So click on the molar volume, click, and then click on done. You can see here molar volume in terms of feet cube per pound mole is shown up here. You can change the units of this the molar volume by going into again to the unit set and find out where its molar volume is. Molar flow, molar volume is shown up here. You can change this one into meter cube per kg mole and then click on OK. You can see here the units of the molar volume is changed here. Now this is fine. Now I want to study some information. So the answer for the question is, what is the molar volume of butane? That is 2.058 meter cube per kg mole. That will be shown up here. Now we want to study something for regarding this molar volume. I want to see if I change the temperature of the stream, what is the effect on the molar volume. Okay, this is what I need to find out. So to find out this thing, what I need to do to study the parameters of temperature effect on the volume, I need to go to case studies. So click on the case studies, which is shown on this window. Similarly, you need to add, there's an add button here. Click on the add button. Now if you look at here, we have two variables. One is called independent variable and one is called dependent variable. In your case, maybe you have only one window where you can add these two variables. If you look at dx over dt, or let's say I will give you simple example here. If you have let me show up. Okay, if I will just, if you, for example, if you have dx over dt or dy, so what is this thing? This is a dependent variable. This is dependent variable. Okay, and what is this thing? Independent variable. Independent variable. Okay, so it means like this variable is changing with respect to independent variable. So the dependent variable is changing with respect to independent variable. So in our case, what we are studying, we want to study the volume, the molar volume with respect to the temperature. How the volume is, molar volume is changing with respect to temperature. Okay, this is what we want to study. So in HYSYS also we need, if you, in your case maybe you have only one window, you add the dependent and independent variables. In my case, I have two separate windows to add to the independent variables. So what I will do, I will add the independent variable. This is my stream name. I select the stream name first, then I write temperature. So temperature is my my independent variable, which is shown in the denominator. Done. So I add the independent variable. Now I need to add the dependent variable, which is again for the same stream. I can type it molar volume, and I will type and I will just put it here. Done. Okay, so I add the independent variable, which is temperature, and I add the molar volume. After you add these two things, you need to click on the case study setup, second tab. On the case study setup, what you need to do is you need to change the information of the independent variable in order to see what is the effect of change of this on the dependent variable. Okay, so here on your screen you will get the temperature, the starting, the current value of the temperature, the starting point of the temperature, the ending point of temperature, and what is the step size between start to the end. What is the step size of the every time they will change. Okay, and based on the step size, it will calculate the different steps. Okay, for example, if I use 500 for the start and 1000 for the end, and if I take 50 steps, then how many steps it take from 500 to 1000. Okay, that will be shown up here. So first I need to see what they have used in the in this case study. So they did basically for a degree Celsius. So but in our case we will do in degree Kelvin. So let's say I want to use 500 for my start, or let's say if I start from 200, not 200, let's start from 500 also and go to 1000. And if I do 10 steps, 10 steps are too many steps, too small steps, so let's say 50. So 11 steps. If I go from 500 to 1000, I need to take 50 step size. The total steps would be 500. Then after this you need to click on run. Once you click on the run button, it should do some calculations, and if you go down you can see here the green bar says success. Okay, this means like your case study is complete and finished. Now you want to see where is the result. You go to the result option, you can see the results are here, but this result doesn't show any, doesn't depict or does not reflect clearly. Okay, but if you put this on a plot, then you can see here the results more clear and more easy to understand. Okay, so what this means is if you're changing the temperature, your molar volume is changing. Okay, so this is the result of increasing the temperature on the molar volume, and this whole process is called case study, which is shown up, just saved here. Okay, so what is the question? The question is you need to study the case study steps. What is the effect of changing temperature on the molar volume? Here they mention in terms of degrees Celsius, but what we did in our example is we use the degree, we use the Kelvin. Doesn't matter, but what is important is like how the changing of temperature will affect the volume. So you need to write it here. From the graph it is concluded that by increasing the temperature, the molar volume, specific molar volume or specific volume will increase. Okay, then this is your home task. You need to use Ping-Robinson instead of SRK equation of state and do the same study. So instead of using Ping-Robinson equation of state, what I'm asking you to do, use Ping-Robinson and give me the result. Okay, so this is what you need to do. So your home task is using Ping-Robinson and follow the same procedure and see what is the effect of using, and then you do case study also, what is the effect of using Ping-Robinson equation of state on the molar volume. If it changes, how much is the change? Okay, there are some questions which is shown at the end. I will ask you to please go through the questions by yourself first before I'm able to I will I will solve those questions. But first you need to do by yourself, so that I will see like you are practicing. Okay, so if you are doing it correctly or wrongly, then I will definitely in the next class I will do those questions. Okay, so this is all for today. Okay, hope you understand. If you have any problem, please don't hesitate to ask. Thank you very much for listening to me. Take care and bye.